Alright, in today's video we're going to be talking about exponential functions. Everything we've done up until this point has been linear. So today we're actually going to be introducing a brand new function, and it's called exponential for a reason. And the key word that I always like to identify when we talk about exponential functions is the fact that it's got the word exponent in it. And the reason that that is important is because an exponential function is a function that has a variable or the unknown value, and that unknown value is actually going to be in the exponent. Okay, so that is super important that the variable is in the exponent. So in order to be an exponential function, the variable has to be in the exponent. So we're going to look at an exponential function in three ways today. We're going to talk about it in an equation format, we're going to talk about it in a graph format, and we're going to talk about it in a table format. And we're going to look at examples and non-examples to compare. All right, so not a linear equation, an exponential equation has a general form just like a linear equation. So exponential functions have that format, that is y equals a times b raised to x. So you can see that that x right here, that variable is in the exponent. So a times b raised to x. So a in this problem is going to represent the y-intercept. So the a is the y-intercept, or the initial value. So just like we talked about with linear, there's an initial value, which is the y-intercept, but with exponential, it is going to be the a value, that number being multiplied in the front. So then we have the b. Now that b is called the base. Okay, so it's called the base for a reason because it is below the exponent. So x is in the exponent, which is the unknown variable, and the base is what is below that. So that base helps us to determine two things. Is this going to represent growth, or is it going to represent decay? Now, if it is growth, okay, so this is super important. If it's growth, then my base has to be greater than 1. So whatever number is in that base spot, if it's growth, it's greater than 1. If it's decay, then it's less than 1, but it cannot be negative, so it has to be greater than 0. So growth is when the base is greater than 1. Decay is when the base is less than 1, but still has to be greater than 0. So what we're going to do is we're actually going to look at some examples and some non-examples. All right, so my first example here is going to be y equals 2 times 3/4 raised to x. I know this is exponential because my x is in the exponent. Now what we want to do is we want to identify a few things. What is my y-intercept, my initial value? That's my a value, that's 2. My base is going to tell me whether it's growth or decay, but that base is 3/4. That's my b value. Now, is this going to be growth or decay? Well, in order to determine if it's growth or decay, I'm going to look at my base. Now, for my base, I can see 3/4 is less than 1, but still greater than 0, so this is going to represent decay. And I know it's decay because it's between 0 and 1. All right, so let's look at another example. So I have y equals 4 raised to x. Now, for this particular problem, I still recognize that this is exponential because my variable is in the exponent. So in this exponential function, there are a few key things that we've got to be mindful of. The first thing is when I look at my general equation, I have an a times a b. So my a times my base. Well, my base is 4. How do I know? Because my 4 in my base is below that exponent. So where's my a value? Well, we have to have an a value. My a value cannot be 0. So if I'm talking about my a value, then I'm talking about what's being multiplied in the front. Well, anytime we don't see the a value, it's automatically 1. So my a in this problem is 1. My base is 4. And this problem is going to represent growth. And the reason it's going to represent growth is because my base is greater than 1. So this one is going to represent growth. Base is greater than 1. All right, so let's look at another example. So I have y equals 5 times 5 over 4 raised to x. Now, the most common mistake that students make with a problem like this is they'll look at the base and they'll draw some conclusions without actually investigating. So I should be able to see that my initial value is 5 and my base is 5 over 4. And a lot of students are going to say, oh, well, 5 over 4, that's a fraction, that's got to be decay. A fraction does not represent decay. If I actually take 5 over 4 and I divide that, I get that my base is 1.25. Well, my base of 1.25 is greater than 1. So since it's greater than 1, this is going to represent growth. So just be careful when you're looking at these types of problems. Make sure, is it greater than 1 or less than 1? Okay? So what are some non-examples? So non-examples are obviously not exponential, but we're going to talk about why they're not exponential. So my first non-example, y equals 5x minus 2. So when I look at this problem, this is linear. I know this is linear because my value, my m and my x are being multiplied. In order to be exponential, my x needs to be in the exponent. All right, now this is probably one of the most common problems that students get wrong. They see right here in the exponent that there's a 2. And they're like, oh, that's got to be exponential. But my exponent has to be a particular piece of my problem. And remember, the exponent needs to be the variable. 2 is not a variable. My variable right now is right down here in the base, and we don't want that variable in the base. This is actually called a power function, and we'll get to this later on. But this is not exponential. In order to be exponential, my exponent needs to be a variable, okay? And then, of course, I could have just a y equals 10. So y equals 10, again, there's no exponent up here. There's no variable in my exponent. So this is not exponential. Now we're going to go talk about our next thing, and our next thing is going to be our graphs. So we actually have particular shapes for all of our exponents, just like we have particular shapes for linear. So when we're talking about exponential growth is going to have a J shape. Now, when I do my J shape, it's going to have, you're talking about exponential, this long tail is where it kind of steadies out because it's never going to go into that negative side, which we talked about earlier. So we're going to have this long tail and then it's going to shoot up exponentially. And we're going to talk about more about what that actually means in a little bit. But today we're just talking about how to identify the key pieces of all the representations. All right, so then we have decay. And decay is actually going to be L-shaped. So when I look at decay, it's going to almost look identical except for it's coming from the other direction. So it's going to start high and then it's going to level out at the bottom. So when I look at these two, I can see if I read it from left to right. So you read a graph from left to right just like you read a book. So left to right, I can see that it's increasing. So it's growing. For decay from left to right, I can see it's decreasing. So since it's decreasing, it's going to be decaying. Okay? So growth is J-shaped, decay is L-shaped. So some examples that are not exponential, just from the unit we just got done with. If it's linear, obviously that's not exponential. We need something that's going to be have a rapid increase. It's going to have that J shape, or it's going to have a rapid decrease, which is going to have the L shape. Or what we're going to talk about later is actually going to be a power function, which has got a U shape or an N shape, depending on which direction it's going. But neither of these are going to represent an exponential. Exponentials are J and L shape. And finally, we have our tables. Now, our tables are very important, okay? When we did linear functions are when my values are adding by the same amount each time. So I'm going to start with a non-example just as a reminder. So if I have a table and I'm comparing how it is changing over time, I'm going to be looking at how the amount that I'm adding or subtracting. So when I look at this particular table, I can see that I'm changing by adding 2 each time, just like I'm adding 1 here. So we're talking about that rate of change between each value. So I can see that my rate of change is linear because my slope is going to be 2 over 1. So this is a linear function, so this is not exponential. Well, what makes it exponential? Well, just like linear is when it's being added or subtracted each time, exponential it's when it's going to be multiplied. So the independent or the y value is going to change by multiplication. All right, so it's going to change by multiplication. So let's look at this particular example here. As I'm looking at this example, I can see that we are going to be changing by multiplication. Now, the reason I know it's by multiplication is because from 2 to 4, I would have to multiply by 2. Now, if I were adding, I would add by 2, but to get from 4 to 8, I couldn't add by 2. So I would be multiplying by 2 each time. So that multiplication is going to represent exponential functions. So again, multiplication is going to represent an exponential function. Now, the other thing that we also are going to be looking at is what happens if it's decay. So this would definitely be growth. And the reason that this would be growth is because my base is increasing by 2. That's the number it's being multiplied by. And my base is greater than 1. All right, but what if my table is not growth? What if it's decay? So when I'm looking at my table here, looking at this function, the first thing that students are going to identify is the fact that these values right here are going down. So since they're going down, this should represent decay. And I can see that it's changing very rapidly. So I can see I'm starting at 162 and I'm already down to 6 by the time I go 3 steps. So this is going to most likely represent exponential because exponential is going to represent that rapid change. Linear is a constant change. So it's changing by that constant amount each time, where exponential is being multiplied, so it's going to change much more rapidly. So the first thing that most students are going to see is they're going to see, okay, from 162 to 54, we're going to be dividing by 3. We're dividing by 3. We're dividing by 3 from 18 to 6. But we cannot divide by 3, okay? We have to represent everything as multiplication. So we need to change this so that it is the multiplication of the reciprocal. So we're going to multiply by the reciprocal. So if I'm dividing by 3, so dividing by 3 is the same thing as multiplying by 1/3. So my base in this problem is 1/3, and that's going to represent decay. And it's going to represent decay because it's between 0 and 1. It's less than 1 in this particular problem. More example like this just to make sure we are clear and we understand. Particular table, again, I can see that I'm decreasing here. And when I initially look at this, I can see that we are dividing by 2 each time. But again, we cannot represent this problem by division. We have to change the problem so that it represents multiplication. So we're going to change it, instead of dividing by 2, we're going to change it to multiplying by 1/2. So this problem is going to represent decay. And we know it represents decay because my base is 1/2. And that means that it's between 0 and 1. All right, so just to kind of summarize to make sure we're all on the same page. So when we have our equation is our general form is y equals a times b raised to x. We know it's exponential if the variable is in the exponent. So if x is in the exponent, and it may not always be an x, it may be a t, it may be an m, as long as the variable is in the exponent. A represents the initial y value, or the y-intercept, and B represents the base. The base tells you whether it's growth because it's greater than 1, or decay because it's between 0 and 1. So then we have our graphs. Our graphs, we have growth. Growth is going to be J-shaped. Decay is going to be L-shaped. And then we have our tables, and exponential functions are going to be represented by multiplication. So the number that we're multiplying by is our base, okay? So since we're multiplying by 2 here, we know that that's growth because it's greater than 1. So when we're looking at this one, we were dividing, but we still have to change that to multiplication. But that base is going to be 1/3, so that's going to be decay. Just like down here, we were dividing by 2, so we're going to change that to multiplying by 1/2, and that's going to represent decay. If you have any questions, please don't hesitate to contact us.